in lecture on Wednesday, we finished off looking at what species would be in solution if I put sodium fluoride in. And then we determined what the pH would be of a 0.5 molar solution of NaF. Now let's talk about this thing called the common ion effect. I'm going to put cadmium sulfide in water, and I'm going to produce cadmium 2 plus and sulfur 2 minus ions. If I were to add cadmium 2 plus, tongue twister, by adding something like cadmium chloride, do you think that will impact the equilibrium? And if so, is it going to shift it to the left, to the right, or you don't know? Pause and think about it. If I add cadmium 2 plus, for whatever reason I can't say CD 2 plus, if I add cadmium 2 plus, that would add to the products. And remember, we did our initial equilibrium expressions, and we talked about products over reactants, S2 minus, that would be over my cadmium sulfide, which is a solid, which is equivalent to 1. So we just leave that be. And so if I add cadmium 2 plus ions, then I'm going to have something greater than K. That means for this one, Q would be greater than K, which means I'm going to shift equilibrium to the left. What impact is that going to have, do you suppose, then, on the sulfur 2 minus ions? Do you think the concentration of sulfur 2 minus is going to increase, decrease, or stay the same? If I am shifting equilibrium to the left because Q is larger than K, then that means I am going to decrease the amount of S2 minus I have. It's going to go down. And a decrease. Simply because I'm shifting from the products towards the reactants, so then my S2 minus is also going to decrease. This impact is what's called as the common ion effect. If I add something that is soluble, and that thing has its ionic components that are part of the concentration of the initial solution, I'm going to shift the equilibrium back towards the reactant side and away from the product side. So let's take a look at that. If I have this lead chromate, or lead 2 chromate rather, and I add that to solution, and that gives me lead ions and chromate ions. So that's what's sitting in the beaker. And if I add, flask, if I add like lead nitrate, what do you think is going to happen? Do you think I'm going to get more PBr, the lead chromate dissolve? I'm going to get a precipitate out, can't tell, or nothing happens. Let's see. If I'm adding my lead nitrate, I'm going to end up with my Pb2 plus NO3 minus. So the NO3 minus isn't really doing anything to this, but the lead 2 plus, I'm adding it here, so I'm shifting equilibrium back this way. The only reactant I have in this case is the solid. So the word that we have for that is that I'm going to precipitate out solid from that solution. Let's think about this in terms of Ka and Kb. What I want you to do is to pause the video and then write out expressions for A. So for HCOOH, ammonia, I should say that carboxylic acid, ammonia, and sodium chlorate. Tell me what you get. Okay, let's write them out. If I have HCOOH, the carboxylic acid, aqueous, and I add that to water, what am I going to get? I'm going to get, well, this hydrogen that is attached to that oxygen. So remember, carboxylic acid is a weak acid. So it's going to donate a hydrogen to this H2O water molecule. It's liquid. And that's going to give me H3O plus. So what do I have left here? This is my other ion. So even if I don't know what the charge is on that, if I know that hydrogen has a charge of +1, that tells me that I'm going to have HCOO minus. Cool. For this, I'm doing my phase labels. For ammonia, we've done that one a whole ton of times. So I'm going to put ammonia into water. And what can happen here? Well, I need to remind myself that that means that there's a lone pair on that nitrogen. I'm not going to give up a hydrogen on the nitrogen. That's a pretty stable species. But what can happen is I can get a hydrogen from the water donated to the nitrogen. So I get my NH4 plus, what have I done? I've taken a hydrogen away from the water, so I have OH minus. So I've made a basic solution here. That's a B, not a D. A basic solution here. I have an acidic solution here. I generated H3O plus. Highlight that. And on this one, I've generated hydroxide. What's going to happen here? What are my two ions? Well, if all else fails, the one thing I can look at, and for anything that I immediately recognize, so either a polyatomic that is obvious to me, or for like any of your metals or your halides, because you know what those are going to break into an ion. So that means that I'm going to have Na plus and plus CH3OO minus. So if I add that to water, honey, let's see here. This is broken into two ions, and that means that I have the sodium ion, and I need to decide if the sodium ion is going to do anything with water or if it's not. And the one thing we were emphasizing in lecture today is that sodium would form sodium hydroxide, which is one of our strong bases. So that reaction is not going to go in reverse. Therefore, the reaction that we're going to concentrate on is the fact that this ion, this CH3OO minus, can accept a hydrogen. So it is acting as a weak base. So that means I'm going to make, oops, let me write it. Oh, that's fine. I can go like this. CH3OOH. And I'm also going to generate OH minus. So I've taken a hydrogen from my water and added it to that negative ion. So I have made this thing basic. So let's see what's happened here. I'm starting off with an acidic solution, a basic solution, and a basic solution. Oops. Okay. Now what's going to happen if I add the B options on each of these? Is it going to shift equilibrium to the left and the pH up, equilibrium to the left, pH down, equilibrium to the right and pH up, or equilibrium to the right and pH down? So pause and come back. All right. If I add this, what's going to happen? I'm going to have a potassium ion and HCOO minus. Those are the two ions. This one here with two ions, what am I going to get? NH4 plus, ammonium and bromine. And then this one is just the exact same thing, actually, we had going on over here, right? So I'll have CH3COO minus and H plus. Or, because this is a weak acid, I can think of this as its entire thing, and that some is going to dissociate going to the left or to the right. Okay. If I add potassium, that would make what? A strong base. So nothing's going to happen with my potassium, but the HCOO, well, I have that ion here. That means that I would shift equilibrium to the left. And if I'm shifting equilibrium to the left, I'm making less hydronium. So if I'm making less hydronium, pH will go up. This one, if I put ammonium in here, I'm going to shift equilibrium to the left. My hydroxide concentration is going to go down. Therefore, my pH is going to go down. If I add the acid here, my weak acid, my carboxylic here, well, that's just straight up what I made from dissociating that sodium, right? So that means I'm going to shift equilibrium to the left. This was a basic solution, so my pH is going to come down because my hydroxide concentration is going to decrease. Okay. The formic acid, it's this thing that happens when ants bite you, that nasty little ant bites that hurt like a Dickens. And I want to look at what's going to happen if I have formic acid, that's this HCOOH, in sodium formate. So tell me, is the formic acid solution going to be acidic, basic, neutral? Can't tell. Well, the nice thing about this formic acid is that it has the word acid in it. So that means that my weak acid is going to break an oxygen-hydrogen bond and form H3O+. So this plus water is going to go to my H3O+, and then plus that ion, the anion. So I want to remind or show you some ways of writing our weak acids and our weak bases. One of the things that we can do is go HA minus, where, sorry, not HA minus. We can go HA going to H plus A minus to show that, it should be a minus, to show that I have a weak acid and some sort of cation that are going to dissociate into in some small quantity my H plus and my A minus. So that A minus can be anything. That can be this conjugate base. It could be some of the other conjugate bases that we've made. Previous slide. Yeah, it's actually the same darn conjugate base. So if I add formic acid, I am going to make the solution more acidic. If I add this sodium formate, what do I get? I'm going to get Na plus my formate, HCOO minus. And if I add that to water, it should look like the one we just did on the other page. This is a proton acceptor. So I'm going to get HCOOH. Kind of look like my formic acid over here. Plus what? I have donated a proton, the OH minus. So this is going to make it basic. But notice I have a conjugate acid and a conjugate base, right? So the conjugate base, the conjugate acid of my weak base, of my sodium formate, is the acid, the formic acid. And the conjugate base, the conjugate base of my formic acid is my sodium formate. This kind of solution is this thing that we call a buffer solution. It means that I have the conjugate base and conjugate acid of each compound in solution. And what's cool about these solutions is that they are resistive to change. I think I'm going to stop there and pick up on the next video.